Hi, welcome to the ZP Developer Zone. So we like to do this Developer Zone once a week, and it's really answering just technical questions that have come in during the week. So let me jump straight into it, and to say today is not actually the 23rd of June 2024, but I sort of starting to find it's actually easier to go slightly earlier because otherwise it's a Sunday morning and it's slightly easier to do this of a Saturday evening. That said, let me go forward, and also we often like to do this live. I'm just having a few problems with my internet and it's super slow, so I'm going to record it and upload it. That said, let me go forward. So questions, somebody's very interested in biofilms, how to detect them using electrochemical methods. I suppose I'm just going to very quickly put my hand on this and say I will talk about the SensiAll platform. I'll put my hands on these and just talk about these cartridge screen printed electrodes. And I believe very strongly you will be using those to actually determine your biofilm. And I realize as well there's also an app on here called, when I say here, I mean on my phone, called SensiAll. I'm just bringing it up now. So you will be installing this on your phone hopefully fairly shortly. That said, I'll go forward with the webinar now. Anyway. By the way, so that's question number one. If you're question number two, which is glucose signal versus area of electrode, just jump to that part of the video. It'll probably be around in about 10 minutes. And if you're question number three and you're interested in electrochemical cells, then jump to that part of it. So 3 questions tonight. I'll try and go quite quickly. I'm just going to do a quick blurb on upcoming webinars. So we do have if you're interested in point of care, and when I say point of care, so I will be using this particular device, the SensiAll, to discuss really doing R&D science in a bit. In fact, if I just pull this out of the way, and I've realized I've got a series of QR codes in front of me. These QR codes are actually really useful because it allows this instrument, using this app, to go between. Do I want to do amperometry, open circuit potential, impedance spectroscopy, linear sweep voltammetry, cyclic voltammetry, or square wave voltammetry? Or do I want to be biosensors, glucose, chili, ginger, potassium, pH, nitrate? So this one particular device, using the app, I can actually go between being a lab instrument, so the person who wants to, for example, measure a biofilm, then they can use it in that context. But people then who want to maybe just do lab experiments, they can use the amperometry, linear sweep, etc. Or some people who want to actually use it in product development can actually use it as well. With that said, let me go back to my slides and just say there's a webinar actually on SensiAll on the 11th of July. So we do with our webinars, we often do 2 webinars. One in the morning and one in the afternoon, because that way it gives more people, I want to say, more time to actually come to the webinar. Just want to show you something very quickly, actually on my phone. Just a FYI, question number 2 is very interested in CGM. So I'm just going to go and I just scrolled up there very quickly just to show you that I could actually bring up amperometry very quickly. Question number 1 is quite interested in biofilm, so I got a suspicion that they would be most interested in impedance spectroscopy. So this, in fact, I can make Bluetooth connection with the device, and then it's made Bluetooth connection, so I can control that device through that app on my phone. So come to the webinar; it might be super interesting. We're also doing one on wearables. As I say, we're kind of I haven't really said it, but at ZP we're super familiar and experienced, I would say, with things like wearable biosensors, including CGM. I've got a CGM here now. I'll be talking about the mathematics. There's a filament on this CGM where all the glucose sensing takes place. And I'll be talking about the maths behind that shortly. Particularly, I'll probably be focusing in on the area of electrode that kind of governs that signal strength. So if you're interested in wearables, there's a wearables webinar on the 9th of July. Again, one in the morning, one in the afternoon. This one is applicable to academia. So at ZP, we're really good at translating academic research into products. So even with that, when I'm thinking about the biofilm question number 1 today, this device, so for example, if somebody wanted to make a measurement of nitrate, they could use the QR code for nitrates, but if they wanted to do some lab work around nitrate, they could, for example, use open circuit potential here. So it's a very good device. It's very good for translating from pure research into actual application. So that webinar on the 25th of June, which is actually just about 3 days away, should be quite interesting. 1 in the morning, 1 in the afternoon. We like to cover all the time zones. The morning one works really well for Asia, Australasia, India in particular. We get a lot of attendership from there. And then 1 in the afternoon works well for Europe and the Americas as well. Question number 1 is about biofilm. So this is going to probably watch this webinar, I would say, or this video on a screen and get your phone out, because there's a QR in the app. Well, first of all, I want you to install the app. So first of all, do this. Scan this QR code. If you're on Android, scan this QR code. It'll put an app on your phone. It'll be called Sense It All. If you're on an iPhone, scan this QR code. It will install an app from the App Store on your phone. And then try this demo. Try screening this amperometer. I might just do that myself. Yeah. So I've now got amperometry on my phone. Let's try open circuit potential. So I'll just scan open circuit potential. Now I've got open circuit potential on my phone. Electrochemical impedance spectroscopy. I think for biofilms, EIS is a good idea. What do we got next? Linear sweep voltammetry. Whoops a daisy, I've got to scan the code first of all. Now I've got linear sweep voltammetry on my phone. Let's do cyclic voltammetry. Let me just go back to that. I'll just scan cyclic voltammetry. Now I've got cyclic voltammetry on my phone. And then finally square wave voltammetry, one of my sort of, I want to say one of my favorites, but that may be a bit, I don't want to have favorites, let's say. So let me just scan that. Yeah. And now I've got square wave voltammetry on my phone. So if you install the Sense It All app on your phone, then you will be able to follow along with that demo. And every time you click it, you'll get a new method, let's say methodology available to you. What you will require then is, unfortunately, is hardware. You will need, and I've put a link to it, some cartridges. Here are the cartridges. You can buy those online, and you will also need hardware. And I will just put my hand back on the hardware here, and you can use that then in biofilm monitoring or biofilm analysis. What I'm imagining is that if you put a solution on there, initially I should have done whoops a daisy, I should have changed screen slightly. So let me just change screen slightly. What I'm imagining is that you have this cartridge and you put a solution on there. As that solution grows, or sorry, as that biofilm develops, then it will actually start impeding the electrodes, and you'll be able to pick that up either using amperometry, or you should be able to pick it up using impedance spectroscopy, or you should be able to pick it up with linear sweep voltammetry. I'm showing you the methods that are sensitive to, let's say, resistance. Biofilms are generally resistive elements. They'll increase the resistance, and any of these techniques that I'm now, cyclic voltammetry, they'll all be impacted by an increase in resistance. Maybe the best one for you is actually EIS, which I think I did. I did have that up there as well. So I think EIS will be the best one for you. So I think you need hardware, you need sensors, and I suspect that the film will grow. It will end up blocking the electrodes, and you'll be able to pick that up, for example, through EIS, electrochemical impedance spectroscopy. Now I'm going to change gears slightly and go to CGM, continuous glucose monitoring. As I say, I've got a few CGMs in front of me now. Not that they're super relevant to actually the mathematical derivation, but maybe they're relevant in terms of when I'm talking about CGM, I'm talking about this kind of technology. I'm super biased, but at ZP we actually have CGM technology that we ended up, we've we've bought the IP. It's 50 patents, and this is something that we license into our client projects. That said, I'll go forward with the mathematical modeling, I should say. I'm going to have a particular focus, I would say, on the area part of these functions, so the area of electrode, because that's where the kind of questioner is most interested in. That said, let me go forward. So we're talking about CGMs. I'm first of all going to describe the kind of the sort of some of the fabrication, because then I can, having described the fabrication, then the equations may be make a bit more sense. So I imagine you've got some inert material. That's your kind of what you're going to eventually build your glucose sensor upon, and you've insulated it in some way, and then you've opened up a particular sort of known area of electrodes. Now that the signal is proportional to that known area of electrode, and I will have equations in a minute for that. So the electrode is really here because this is the known area that you've opened up in that insulator. Now this is the electrode surface, and this is distance from the electrode. So you're sitting in some solution of electrochemically active molecule. I'm keeping this very generic at the moment. And at t is equal to 0, you're applying no voltage. So there's no current flowing, and there is no consumption of this electrochemical material. Now with bare electrodes that are not what they call microelectrodes. So if you have an electrode that's more like 1 micrometer in dimension, it will act like a microelectrode, and actually it can reach steady state quite readily. Electrodes that are on the millimeter scale are acting what we call macroelectrodes, and they are not intrinsically steady state, but steady state is an important word that we'll be coming back. I'll be coming back to in a minute. Now after t is equal to 0, you've turned on the voltage, and what will happen is you'll get some current. But in a non-microelectrode scenario, and I would say that anything with a length scale of millimeters is really not a microelectrode, then as time increases, the current decreases. What you're doing is you are consuming the electrochemically active molecule at the surface of the electrode, and it's only got diffusion that's bringing it in. Diffusion is not necessarily that fast a process. So in fact, you're depleting material, and the current, as material disappears, then current diminishes. Now, this is because we are depleting material. They call this equation, I am an electrochemist, but I do feel like I'm different because I think electrochemistry is a real practical science, so I like to talk about the applications rather than just the science itself. But this is governed by something called the Cottrell equation, and it just says that current falls as a function of the square root of time. But I'm going to say in the world of CGM, the way we do our experiments, we actually set up steady state systems. So this is not a steady state system, but I will give you a steady state system. So I want you to imagine that, in fact, now I'm actually going to stir that solution. I'm going to put a stirrer bar in there, and that's going to change that current profile, because in fact now I've got steady state current. Why have I got steady state current? Because I am no longer depleting the material out my electrode, because I'm stirring, or I'm shaking, or I'm flowing enough to keep on refreshing material at the electrode. Now let's get to the equation. So when I've got steady state at a bare electrode, my current is proportional to n, number of electrons. This is something you can't control. It's only something you can know. You can know it by knowing what molecule you're oxidizing. F is Faraday's constant. It's the charge associated with a mole. I know I hate that term, not hate, units of moles. Chemists love them. It's basically telling you how many atoms you've got in a certain mass of material. And then we're telling you how much charge is associated with that mole when I talk about Faraday's constant. Now the question is very interested in area. Area comes into this equation. So my current, number of electrons, which you can't control, it's just intrinsic to the chemistry that you've put into that solution. F, Faraday's constant, it's not something you can control. Area is what you're manufacturing. Mass transport in this bare electrode is how you set up the experiment. So understand that if you have a jig and you've got several electrodes in there, and the mass transport is different in different parts of that, let's say, test fixture, then that's a problem, because it's actually km that's the variable, and not necessarily like something like the area or something like that. So I is equal to N, number of electrons, Faraday's constant, area, which you manufacture, Km, which you control through your experimental setup, and C, which is the concentration of the electrochemically active molecule. If I put the units for I is current, N is an integer, there's nothing you could do about it, it's just number of electrons, so it's an integer. 1, 2, 3, 4, 5, you know, obviously I don't mean to tell you what an integer is. F, charge per mole, which is 96,485, or just call it 100,000, it's easier. Coulombs per mole. Area is meter squared. I don't, when in reality, when you're talking about glucose sensors, we're already down in millimeters, but area is meters squared. Km, mass transport, is meters per second. So it feels to me like that's really like a velocity, or maybe I should say a speed term. And finally we have concentration, which is you got to be careful because it's in moles per meter cubed. But if you actually take all those units and put them into this equation, you're going to find that everything cancels except for coulombs and per second, and coulombs per second is amps. So that's how not how I know the equation is correct, but the equation is sort of intrinsic. The equation is current is equal to number of electrons times Faraday's constant times area times mass transport times concentration. So if you were making products, let's say, you would put a molecule into there, so that molecule would end up defining C, because that's the concentration you put that molecule in, and that molecule will end up defining N, number of electrons, because that's how much electrons it can give up, or it can take up or receive. F is Faraday's constant. It's just really, Faraday's constant is a good way of going between moles and charge, and then you're back into the sort of electronics domain. And then area is the thing you're manufacturing. But if you have jigs and the jigs have variability in the mass transport, that's going to confuse you because you're not sure if it's area that's the problem or mass transport is the problem. Right, I'm now going to start layering on the layers that turn this bare electrode into a CGM, into a continuous glucose monitor. So the first thing we're going to put on there is, I've sort of done this in a slightly wrong order, but it's actually a membrane. So I want you to imagine our surface, our electrode surface, and we've got distance from electrode, but I've actually put a membrane over there. Now I'm going to put my electrochemically active molecules into a solution. You must understand now that not all the electrochemically active molecules get to the surface. In fact, only a few of them get to the surface, because only a few of them actually end up getting into the membrane. So we end up, so at t is equal to 0, nothing's happening. But once t is above 0, then I've turned on the voltage and I get a current. But understand now that relative to the bare electrode, first of all, the current is lower. Why is the current lower? Because actually I'm blocking the surface with this membrane. But that lower current also means that only a few molecules of the entire population are getting into that membrane. So if I consume a molecule, it doesn't matter because there's plenty of other molecules just outside that membrane ready to pop in. So in fact, once you put a membrane on an electrode, it doesn't act like a transient where the current's falling with time. No, because I've got a large number of molecules ready to replace what was in the membrane. So actually you get steady state current. Now the equation for this is I, and I'm just going to make myself disappear for a second. I is equal to number of electrons, F, Faraday's constant, A, area of electrode, the thing you manufacture, Km, your mass transport, this is the thing you've got to really be careful about controlling in your experimental jig, C, your concentration of electrochemically active molecule. So nothing has really changed, they've all got the same units as before. I've made a mistake here, by the way. I put that as Cm, I should have just put it as C. But understand now that mass transport, that term earlier on that I kind of called a velocity, or I wasn't sure to call it a velocity or a speed. It actually means something a little bit different this time. It actually means the effective diffusion of the electrochemically active molecules through that membrane divided by the thickness of that membrane. So that's the thickness here. If you make that membrane thick, then Km goes down and the current goes down. If you make that membrane thin, Km goes up and the current goes up. just out of interest, in glucose sensing, it's not necessarily good to have a lot of current, because a lot of current means a lot of consumption of glucose, which means you'd start doing strange things in the sort of micro pockets around CGM. So I don't like necessarily having a lot of current in my glucose sensor. But KM this time, earlier on I was sort of saying, when it's a bare electrode, if you flow faster or stir faster or shake faster, you're essentially getting the liquid to move faster through that cell, and KM will, the faster KM is, the more current you've got. This time round, it's not so much sensitive to how you're mixing or stirring. It's actually more sensitive to that membrane, which is kind of what we want. It's proportional to the membrane itself, and that's kind of reflected in how well the molecule is diffusing through that membrane. So if you had porosity, a porous membrane rather than DF could in fact end up being larger, and if you make the membrane thicker. So you've got DF tells you something about the way the electrochemically active molecules are interacting with the membrane, and D tells you, D is the thickness of that membrane. So the thinner it is, the more current you end up getting, I should say. I'm now going to start building my glucose sensor up a bit more, because I actually have to talk about the enzyme layer. So not just the polymer on top, or the barrier layer as that's sometimes referred to. I'm going to talk about my enzyme layer. So I don't want to be pedantic, because I know the people I'm sort of addressing are very knowledgeable on this subject, but we have glucose going into that enzyme layer, and there's a reaction, but the reaction ends up giving us a molecule called hydrogen peroxide. I want to bring this hydrogen peroxide into my equation shortly. So it's hydrogen peroxide that actually, in a generation 1 glucose sensor, is actually what we end up detecting. How much hydrogen peroxide is there at any one time? There's the hydrogen peroxide available at any one time. Its concentration is proportional to K. K, I should have written this more clearly, has a value between 0 and 1. 0 means you've got no reaction going on, so the concentration, doesn't matter how much glucose you have, let's say the enzyme is inactive, then the K there would be 0. So K times the 0 times the glucose concentration is still 0. If K is equal to 0.1, if I've got a glucose concentration of 5 millimolar, then 0.1 means that I would have a concentration of 0.5 millimolar of hydrogen peroxide. If K has a value of 1, for example, then if I had 5 millimolar of glucose, I've got 5 millimolar of hydrogen peroxide. In reality, K will have a value more like 0.1 or less. You can sort of think of that as an efficiency term, but because in the end, a glucose sensor is not directly monitoring glucose, it's actually indirectly measuring glucose through it's the production of hydrogen peroxide. And so I've written you here a term that couples the hydrogen peroxide and glucose concentration. So if I take my fictitious CGM and I put my enzyme and my barrier layer on it, then my current is proportional to N, number of electrons, F, Faraday's constant, A, area of electrode, Km, which is sort of mass transport, and C. But in reality, C is actually, it's not, now I can sort of say, well, C is actually K glucose times C glucose. Now, I'm going to say that actually the only thing that is either not known, when you look at this, is actually current is proportional to glucose. And N is something that is known, F is something that is known, A is something that you manufacture, so should be known. Km is something that you essentially manufacture, because that's how you make the polymer and how thick you make the polymer. K is really also something that you control, because we essentially control the electrochemistry, because we're the ones who put the enzyme in there. So it's just to kind of say that a lot of things are actually kind of known or controlled, and so in the end, I is proportional to the concentration of glucose. Let's do a glucose experiment now and try and sort of bring all this together. So I have my electrode, I put my enzyme and barrier layer on it, I put that into a solution, and I measure current. So this is current in 0 millimolar of glucose. Then I add some glucose, and I get a step in my current. Now ZP does a lot of this work, and we actually do end up with steady states. The fact is this current is demonstrating, I would call steady state. But I measure the steady state current. Then we add some more glucose, and we get another step, and we measure the steady state current. Then we add some more glucose, we get a step up in current, and we measure the plateau, and we call that the current. So we have current versus concentration, then the last addition, and we end up with a straight line like that. Now that straight line has a slope, or you can call it a slope or a gradient. Sometimes we call it a sensitivity in the CGM world. So the sensitivity of my electrode here is in nanoamps per millimolar. But that sensitivity is actually, inside of all that sensitivity is all these terms, N, F, A, K, M, K, glucose, like that. So in fact, all of those are in there. So I is proportional to sensitivity times glucose. But in simple terms, if you double the area, you will end up doubling the current. It's not always a good idea to have lots of current in a CGM application. Just be cautious, because I have had people who want all the signal in the world, and it leads to some strange phenomena. But that said, what's the equation behind a CGM? This is the equation behind a CGM. Sometimes it may be very hard to deconvolute, these individual terms. So, in the end, if you manufacture repeatably, then A will be a constant, Km will be a constant, and K here will be a constant, and then you have a repeatable sensor. But those are kind of essentially the three parameters that you have to control in manufacturing in order to have a repeatable, say, production line of glucose sensors. Question number 3. Somebody's very interested in our adapters for adapters for screen printed electrodes. We do have a lot of adapters for screen printed electrodes, our 7mm or our 10mm ones. And this little adapter here gives you a little orifice in which you can then add materials and do chemical reactions. So that is useful, and we do have lots of flow cells. So question number 1, how to detect a biofilm. You need to install those apps on your phone, try the demo. If you get the hardware, then you can end up using something like impedance spectroscopy in order to measure the biofilm development. Glucose signal versus area of electrode. Glucose signal versus area of electrode, they are directly proportional. If you double the area, you tend to double the glucose concentration. Question number 3, we do have a whole range of electrochemical cells, and if you're interested in them, please don't hesitate to contact us. And with that, I want to say thank you. Like I say, I've recorded it tonight just because my bandwidth is up. But if you have any questions, please don't hesitate to, I want to just turn that on. Please don't hesitate to reach out to us. Okay, thanks very much. Take care. Night night.